previous video, we just finished up talking about introducing nozzles and diffusers. Now, one thing we didn't mention there is this idea down here at the very bottom, probably, as we've mentioned before, probably no potential energy change, probably no work, but that's only going to be true if I don't have the most common type of work I might encounter with one of these types of devices would be something like electrical work, for example, right? So if I've got electricity crossing the boundary, some kind of electronic heater, electronic device in here, you're gonna have electricity crossing the boundary in the form of work. Might have heat. That's probably, there's a good chance that's what you're actually going to be looking for in these types of problems is the amount of heat lost or gained or something like that. Okay, the next category of devices is a compressor. Compressors, very simply, compressors add energy. That's it. Where I teach, I get some people in the aerospace industry, sometimes come to, working on a degree, and they a lot of times will call a nozzle a compressor. We're using a different set of terminology. I understand why they do that, but we're using a different set of terminology here. For us, a compressor very simply is a device that adds energy. That's it. It's a very generic device that adds energy. I was taught to kind of draw them in almost like a turbo configuration, similar to what you see in the GIF image there. Oh, no, you don't want the outlet down there. I apologize. Let's just try that again. Um, yeah, I normally draw these kind of in a turbo configuration, meaning that you basically kind of have an outlet on the narrow end and an inlet up here on the broader end. You have some sort of a rotating shaft putting a power input into the device, similar to what you see, right? What you see down here. Let me, one of these times I'll get good at. So right here, you see this rotation. That would be a rotating shaft right here, putting some sort of a power input coming in. Now, you have mass coming in, similar to what you see on the screen there. You have mass coming in, and then it's getting squeezed coming out, kind of a narrower end. In this case, I see the GIF image that I've used there doesn't perfectly demonstrate what I'm trying to explain with my diagram. But this is a common way that we would draw a compressor, just a simple diagram of a compressor. You have mass coming in one place, mass going out another place, a power input. That's really all you would need. Um, a lot of times it kind of gets the material gets squeezed as it moves through. But at the end of the day, compressors are a device that add energy. That's really all we need to know at this point. Now, how that energy increased manifests itself can take a number of different forms. It depends on the fluid, it depends on the construction of the device, it depends on how that energy is getting applied to the fluid stream as it moves through. Again, fluids can be gases, vapors, liquids. It can take a number of different forms. Anything that flows can be considered fluid. Fans and pumps are very specific types of compressors. Again, devices that add energy to the fluid stream as it moves through. A fan on, for example, a lot of times that's a device that's increasing the kinetic energy of a gas or a vapor as it moves through them, mostly gases. A pump, on the other hand, are often applied to liquids in the primary purpose of that kind of device because liquids don't compress. You really all you're going to do is you're going to increase the pressure from the inlet to the outlet. So that's kind of the primary goal of a pump. But in both cases, you're going to add energy to the fluid stream. Now, some compressors you'll see a significant increase in kinetic energy. Some compressors will not. That will be We're going to talk about how do you determine from the problem statement and what's given and what you know whether I need to worry about the kinetic energy change or not. Unlike, for example, a nozzle or diffuser where there you are going to have a kinetic energy change. That is the goal of these devices, is to change the kinetic energy. With a compressor, and we're going to talk about turbines next, with a compressor, you may or may not have a significant increase in kinetic energy. Depends on the device. And you're not always going to know that in a Thermo 1 class about the device, what kind of compressor it is and how that increase in energy really ends up manifesting itself. All we're going to have is the information provided, and that might be enough to figure out the kinetic energy increase. It might be where we just have to say, well, you know what? Um, and we talked here about the enthalpy change is always going to be on the order of or larger than the kinetic energy change. Sometimes there's three or four greater than signs here where the enthalpy change is kilojoules and the kinetic change is joules. But in all cases, we're going to be dealing with really small devices where microjoules at best are going to be the change in potential energy. So we're going to neglect those most of the time. Okay. Now, but again, it depends on the device, and we're going to talk about how do you go through the problem statement, what it says, and figure out what we actually need to look at. Turbine or turbine, however you want to pronounce it. A turbine is a device that extracts power or work by slowing down or expanding fluid. So this is a device that very simply extracts work from the fluid. You can have a kinetic change. You might have enough information to compute a kinetic energy change. You may not. Um, this is kind of a dual-sided turbine. This is common to what you would see in an industrial power plant. You would inject high pressure steam into an inlet, and then that's going to move through a set of fan blades, a set of very thin metal blades that are going to spin as that high pressure steam moves through them. It causes these blades to spin, and all these blades are tied to a large shaft. And so here, this image is kind of it looks like a CAD model where they're showing a cutaway diagram where this case would go ahead and be extended all the way through. And when this thing's closed, they've just cut it away so we can see inside it. But this is an industrial sized steam turbine, at least a nice diagram of one. And again, steam comes in the middle, blows both directions, passes through progressively larger and larger fan blades as the material expands. Through that expansion process, we're getting work out, just like we talked about in the piston cylinder. And that as that work is being extracted, as it causes those fan blades to spin, that causes a large shaft to rotate. And so then we can get kind of a power output coming out of that shaft. So again, you have in here mass coming into the middle of this one, and it's going to come out then of these sides. If I'm to draw a turbine, I'm basically going to draw half of this, right? I'm pretty much just going to like draw half of this right here is what I'm going to draw, right? So if I draw half of that, you could draw both sides if you like, but I'm going to draw some kind of device that expands from the inlet to the outlet. And my drawings on the board are normally a little better than this. I'm not great at drawing on this tablet. It's a Surface that I'm using. I'm not great at drawing on it. A lot of times I use a smart board in front of a classroom. Again, the purpose of a turbine is to extract a power output. Okay. So I'm extracting a power output by flowing mass into kind of a narrow end, and I'm allowing that mass to expand and cause components inside this device to extract energy from that mass as it flows through. So you have mass coming in, you have mass going out, and you have a power output. There's probably going to be some heat transfer, although we will often try to insulate these devices to where they don't lose a lot of heat. But you are going to lose probably some. So there's probably some heat transfer. That might be the thing that you're trying to calculate or estimate at least. You might have kinetic energy changes. You probably will. Now the question is it significant enough to be calculated? Well, that's going to depend on what information is given to you. Okay. But this is a common way I would draw a turbine. Again, first step of writing a first law equation, draw your system. This is how I would draw a turbine. You can see how I would draw a compressor. You can see how I would draw nozzles and diffusers. Right. So you kind of get the basic idea that that'll be step one of writing a first law equation. Now, when we simplified and we talked about devices with one inlet and one outlet, notice that all of these previous devices we've talked about, turbine, compressor, nozzle, diffuser, all of these have one inlet, one outlet. You will also encounter some devices where you have multiple inlets and multiple outlets where this version of the first law does not work. You'll have to do multiple, you'll have like H1, H2, H3, H4, or something like that, depending on how many inlets and how many outlets. And you'll have to subtract the end, sorry, you'll have to add the ends, subtract the outs. So we'll go back to the more general version of the first law for steady flow control volumes for these type of devices. So these will mostly come in two main flavors. One will be a mixer. A mixer is any device that has fewer outlets than it has inlets. If it's operating at steady flow, that means at least some of those inlets are getting mixed together to typically a single outlet. So often a mixer has got two or more inlets and a single outlet. Just depends on the purpose of the device. A lot of times in food processing, we'll use steam kettles or steam jacketed devices where we've got a food product coming in and we need to warm it gently, but and not really add anything to it. But what we can do is we can add a little bit of water to it. So we have a concentrated cooler product like soup or something like that coming in. We can inject high temperature steam into it. And that will, number one, warm it and go ahead and number two, reconstitute a little bit. That's a very simple, clean, gentle way of doing that. A heat exchanger. Now, a heat exchanger is any kind of device where often I'm going to have a hot stream and a cool stream. So like the radiator in your car, for example, you've got air flowing through that, often being pushed through by as your car drives down the road. You probably have a fan where if that's not enough or you're sitting idle, that fan kicks in and goes ahead and pushes air through that device also. And that's going to cool then a hot stream of radiator fluid that gets returned back to the engine. And that's how we get the excess heat out of the engine in an internal combustion engine in a modern car. So there you've got a hot stream of radiator fluid, you've got a cold stream of air coming through, and they never actually mix. You're just simply going to transfer heat between them, right? So since you're transferring heat between them, with a heat exchanger, if you've got a separate hot stream and a separate cold stream, and those two streams never actually mix, they're separated by some sort of boundary, some sort of layer, like thin metal or aluminum, or which aluminum is metal, some sort of thin metal that's very good at conducting heat between the two streams. You can either analyze them as a separate system. So you'll have a hot system and a cold system, or you can analyze them as one single system when you do your first law analysis, and either one will be just fine. And we'll talk about both of these when I start working some examples then in some of the later parts of this lecture. If you're in my class, just real quickly, a little bit of bookkeeping. If you're in my class, normally I only post notes for lecture 11. I don't normally post notes for lecture 12 because basically there's enough slides in this presentation to do two full lectures. So I think we're kind of hitting the point where, yeah, we're hitting the point where now we start working example problems. So I've got enough slides at this point to do half of lecture 11 and all of lecture 12 entirely of example problems. So that's what we would do in my class with me. So those of you that are going to follow along with us, that's what you're going to see. I don't know if lecture, there may not, I probably won't make a part 3 of lecture 11. I'm probably just going to start making lecture 12 videos and they're just all going to be examples. So I think that's what we're going to do, but that's what the two together are. All right, guys. Hopefully you enjoy the example problem.